first one, we want to look at the fundamental theorem of algebra. Fundamental theorem of algebra says, if p of x is a polynomial of degree n greater than or equal to 1, then p of x equals 0 has exactly n roots, including multiple and complex roots. Okay, that statement is actually a whole lot simpler than it sounds. It says that if I have a polynomial like this one, x to the fifth minus x to the fifth minus 3x cubed plus 3x squared minus 4x plus 4 equals 0, that's a fifth degree polynomial. There are 5 roots to that polynomial. They may be rational, they may be irrational. They may be complex or they may be real. But there are a total of 5 of them, even if some of them are repeated. So let's look at the process of finding all of those roots. First of all, I might look for the possible rational roots, using the rational root theorem. If I use the rational root theorem to find the possible rational roots, this one's got a fairly short list. I'm looking for factors of 4 over factors of 1, which gives me a list of positive and negative 1, positive and negative 2, and positive and negative 4. So that's my list of possible rational roots. So if I go back and graph this on my calculator and look, because I don't want to test all of those if I don't have to, if I graph them, it looks like probably 1, 2, and negative 2 are roots to this polynomial function. All right? They appear to be roots. So let's find out. Are they roots or are they not roots? Synthetic division is probably the easiest way to do this. And you'll discover that you can do synthetic division one factor after another instead of starting over, and it makes it a little easier. So I'm going to start with 1. That's the first 0 I'm going to check. So 1 goes in the box, and then I take all of my coefficients. 1, negative 1, negative 3, 3, and negative 4, and 4. Long list to start with. First number comes down. There's my 1. Multiply by the number in the box, gives me another 1. Add down, that's 0. 0 times 1 is 0. Negative 3 plus 0 is negative 3. Negative 3 times 1 is negative 3. Add down, I get 0. Multiply by 1, I get 0. Add down, I get negative 4. Multiply by 1, I get negative 4. Add down, I get 0. Okay, so I got a remainder of 0. If I got a remainder of 0, then x equals 1 was indeed a 0 of this function. Well, I have 2 more that I want to check. I want to check for the value of x equals 2 and x equals negative 2. Don't start this over again. You know, instead of starting over again, just put your 2 in a box right here. And then repeat your process. So if I bring the first number down, this 1 comes down, and I multiply by the number in the box. So 2 times 1 is 2, add down. And I'm just going to repeat this process all the way across here. So I get 1, 2, 2, 4, and 0. Look what happens. I ended up with a remainder of 0 again. So I know that 2 is also a 0 of this function. And then we can do this one last time. I'm going to put this negative 2 out here in this box instead of rewriting this whole thing over again. So the first number comes down. So that gives me a 1. Multiply by the number in the box. 0. Multiply by the number in the box. Gives me 0. This number is 1. Multiply by the number in the box, negative 2. Add down, it gives me 0. So what have I got down here at the bottom? Let me rewrite this. This is 1, 0, 1 with a remainder of 0. So I have here a factor that looks like x squared plus 1. So using these zeros, I have x minus 1, x minus 2, x plus 2, and then what I had left over at the bottom, x squared plus 1. There was no center term there, so I didn't end up with an x term. This is factored over the reals. Why do I say that? Well, if I go back and I factor that x squared plus 1, I'm not going to get a real answer. So this is as far as I can go if I want this factored over the reals. Well, so x minus 1, x minus 2, x plus 2, x squared plus 1. What if I go back and factor this? If I factor it, I use quadratic formula, whatever, I end up with my last two factors. X minus 1, x minus 2, x plus 2, x plus I, and x minus I. This is now fully factored and it is fully factored with 5 linear factors. By my fundamental theorem of algebra, I knew that there needed to be a total of 5 roots. 5 x-intercepts? No, not necessarily. In this case, I only had 3 x-intercepts because I had 2 imaginary factors in the bunch. They are zeros, they are solutions, they are roots. They are not x-intercepts because they're not real numbers. Let's do one more of these just to make sure that we have the hang of this. And in this case, we're going to look at a couple that give me not complex roots, but irrational roots. So let's begin with the polynomial g of x is equal to x to the 4th plus 2x cubed minus 4x squared minus 7x minus 2. So there's my polynomial. I'm going to graph it on my calculator and figure out what looks like it is probably a 0 of this polynomial. Now I could get my list of possibles, factors of negative 2 over factors of 1. So I don't have a very long list here. Positive, negative 1, positive, negative 2. It looks like negative 1 and 2 are my roots to my polynomial. They appear to be zeros. Don't know that for sure. How many zeros, how many roots am I going to have altogether? I'm going to have 4 according to the fundamental theorem of algebra. I need 4 of those because that's a 4th degree polynomial. So let's set up our synthetic division and see which ones work out. I'm going to start with negative 1. It goes in the box. My coefficients are 1, 2, negative 4, negative 7, negative 2. First number comes down. And do my synthetic division. Negative 1 gives me 1. Negative 1 gives me negative 5. 5 gives me negative 2. And negative 2 times 2 gives me 0 for a remainder. It is indeed a factor of this polynomial. Worked out nicely. Alright, so let's check the other one. The next one is 2. And I'm going to reuse my list of numbers here. First number comes down. 1 times 2 is 2. Add down. Multiply by the number in the box. Add down. Multiplied by the number in the box. Add down. Remainder is 0. And I get x squared plus 3x plus 1. Now, doesn't obviously factor. So what am I going to do? Well, probably the easiest thing to do at that point is to put this into the quadratic formula. So x is equal to opposite b plus or minus the square root of b squared minus 4ac divided by 2a. Are you singing the song as you write it down? Simplify that and I get negative 3 plus or minus the square root of 5 over 2. Well, look what I got. I got an irrational solution, and it's a plus or a minus, which means I have 2 zeros of my function. The zeros of my function, if I come back and list these, are negative 1, 2, and negative 3 plus or minus the square root of 5 over 2. I could write that as two separate factors if I want to, like two separate zeros. I could say negative 3 plus the square root of 5 over 2 and negative 3 minus the square root of 5 over 2. If I want this fully factored over the rationals, if my instructions say factor this over the rationals, that means I don't want an irrational number in my answer. So factored over the rationals, this would go back to what I had before I plugged this in the quadratic formula. I'd have x plus 1 from this one, x minus 2 from this one, and then I would use this quadratic, because once I solved that quadratic, I got irrational numbers. So factored over the rationals, this factors like this. Factored over the reals, then I can use my irrational numbers, because it doesn't matter whether they're rational or irrational at that point. So factored over the reals, my factors are x plus 1, x minus 2. Now, I'm moving all this to the other side of the equal sign, so the signs are going to change. X plus 3/2 minus the square root of 5 over 2, and x plus 3/2 plus the square root of 5 over 2. That's factored over the reals, or fully factored for this polynomial. We knew there had to be 4 factors. How do we know that? Because this is a 4th degree polynomial, and the fundamental theorem of algebra says they're going to be the same number of solutions, the same number of factors as that degree of my polynomial.